And I'm not sure if it's like the same problem we talked about in class, but there was one where it's like you kind of helped us go along with it, but it was like a power series sum to a function that is analytic at every point inside a circle of convergence. And we know that by definition in problem 2 that R naught is the circle of convergence.
Yeah. That is modulus of z minus z naught is equal to R naught is the circle of convergence.
Yeah.
The circle is the bounding thing.
And then like we kind of went through it kind of like we said partial sums of power series of polynomials, and then some stuff about like use a lemma that a sequence of analytic functions uniformly converge on a simply connected domain.
Yeah.
And then use
Moreira's theorem.
Moreira's theorem. Is that for the same problem? Is that number 2?
So this is what we showed where it converges uniformly on every closed disk, right? So I'm asking you to make the final step of that theorem and say that showing that it uniformly converges on every closed disk, subdisk, I should say, inside the circle of convergence means that it converges pointwise on every point contained inside the circle of convergence, on the interior. That's the thing that you're supposed to prove. So it's the missing step to relate what we did in class to the initial statement of the theorem. Okay, so great. Let's remember where we were last Friday. We skipped over some characterization of poles, so we could talk about essential singularities, just to get that out of the way. So now we'll go back and just say a couple more things about poles, and then we'll do a whirlwind tour of what's necessary to prove the residue theorem, which is this even faster way of computing integrals than what we've discussed so far. Okay, and if there's time left over, I'll give you some glimpse of this thing called the argument principle. Okay? So, right, here's our first lemma, going back to poles, right? So the last thing we proved about poles is the behavior of the modulus of z minus z naught to the L times f of z when z naught is a pole of order m and L is less than m, right? We said that the modulus goes to infinity of that function I just described. Okay, so here's a couple more lemmas about poles. The function f has a pole of order m at z naught if and only if in some punctured disk centered at z naught, we have the following. F of z is equal to g of z divided by z minus z naught to the m with g of z analytic and non-zero at z naught. Okay, so this is kind of what you would expect, right? That you can express the singular nature of f at z naught as having a polynomial denominator, right? So the proof of this is relatively short. Let's go through it. So first, the forward direction, we'll assume f has a pole of order m and z naught. So then what we know is if we consider the function z minus z naught to the m times f of z, we can write this as some function g of z, which has Laurent expansion a sub negative m plus a sub negative m minus 1 times z minus z naught, right? So on and so forth. We're canceling by multiplying by z minus z naught to the m. We cancel all the negative powers of z minus z naught in the Laurent expansion, right? This being the least non-zero coefficient in the Laurent expansion, right? Okay. Then we just set g of z naught equal to a sub negative m, which by assumption is non-zero, right? So clearly this is analytic in the neighborhood, right? It has no negative exponents, and it's also non-zero because by virtue of z naught being a pole of f at, being a pole of f, we know that this coefficient must be non-zero. Right? Okay. So conversely, and before we go on, this is exactly what we did when we redefined a removable singularity, right? When we redefine the function, we just plug in the value at the Laurent series when we cancel out the singularity. Similar procedure here. Okay. So now let's assume that f of z has this representation where g of z is analytic and non-zero at z naught. Okay. So in this case, we must have that g of z is equal to b naught plus b1 v minus z naught plus 2 v minus z naught squared the Taylor series g at z naught. This implies the Laurent series for f near z naught, that is in some punctured disk centered at z naught, must be by the assumption of this formula holding, b naught z minus z naught to the m, plus b1 over z minus z naught to the m minus 1, so on and so forth. So since b naught is not equal to 0, has pole of order m. How do I know that b naught is not equal to 0? This was part of my assumption in going the opposite direction, right? We assumed that g, the value of g at z naught was non-zero. So in other words, if this is the Taylor expansion for g of z, if I plug in z naught to that, I just get b naught, which must not be 0 by assumption. Okay. All right. So, right. So, one more lemma, which we won't prove, but it's important that you see it. And then we'll just summarize everything we've said about isolated singularities as a theorem. Remember, when we started our discussion of isolated singularities, I said that we would come up with some qualitative description of how a function behaves near the 3 different types of isolated singularities. That is, they're characterized, they're defined by how the Laurent series behaves, right? But by the end of this, we'll have some idea of how a function behaves near these types of singularities so that we can classify them without necessarily computing the Laurent expansion. Right? That's the idea. Okay, so one more lemma, which just kind of illustrates that these things behave in a somewhat expected way. Poles behave in somewhat expected way. So if f has a 0 of order m at z naught, then the function 1 divided by f has a pole of order m at z naught. Okay, so think about polynomial. This makes good intuitive sense, right? But remember, now we're just talking about a much larger class of functions. There are lots of analytic functions which are not polynomials. So, furthermore, if f has a pole of order m at z naught, what is the analogous statement I want to make here?
1 over f has a 0, or has, a 0 order m.
Ah, you might think that, but it's slightly more subtle than that. Then 1 over f has a removable singularity at z naught. Now, what happens when I remove the singularity? Then I get what you were saying, okay? And h of z new function that we define as follows: 1 over f for b not equal to z naught, and 0 at z equal to z naught, and a 0 at order, of order m at z naught. Okay, this is just a consequence of exactly what we were just saying. It's not guaranteed that f is a polynomial here. F is an arbitrary analytic function. So you can't just use regular arithmetic for manipulating polynomials. You have to, these rely on computations with the Laurent series, right? Again, I'm not going to prove this, but if you're interested, you should look in the book. It's not that much extra time, but we're really crunched for time. Okay, good. So, right. Let's just quickly record everything that we've said about isolated singularities, just because we'll refer back to that in our development of the residue theorem. Okay? I guess I should make one remark here. This lemma helps you define what it means to have a zero or pole at infinity. Okay, which is section 5.7 of the textbook. How you can do similar analysis of isolated singularities, including the point at infinity, by looking at reciprocals of functions. Right? So this is again something that would be very useful to us in computing certain real integrals that we can realize as the real component of a contour integral. But we're not going to have time to get to that. So yeah, maybe read section 5.7 as well. It's kind of interesting. I was torn as to whether to talk about that or go to the residue theorem. I think the residue theorem is probably more important, but the point at infinity is important too. Okay, anyway. Let's suppose f has an isolated singularity at z naught. Then we can say a lot of things. In the first case, if z naught is removable, this is true if and only if the modulus of f is bounded near near z naught, right? That is to say, in some punctured disk. It's true if and only if f of z has a limit as z approaches z naught. And as we've seen time and again, f can be redefined at z naught. So f becomes analytic Z0. All these, yeah.
Can the singularity be at the very edge of the region where F is analytic, or does it have to be here?
So under our, so when you say at the very edge, you mean on the
Yeah,
boundary?
if you're analytic in some open disk, then could it be on the circle?
So, remember, we talked about how tacit in our hypotheses is that we're looking at a disk or an annulus, a punctured disk centered at Z0. So, the question is, I guess the question you're asking is, can we reside on the boundary of the largest size disk that we can be in? And the answer is occasionally. So there's a theorem proved in the book that convergence of the Laurent series fails necessarily at some point on the boundary. So you have to be judicious in the point that you pick if you want to consider something on the boundary. And this is actually related to analytic continuation. Like at the points where it does converge, you can continue the domain outside that, right?
Yeah, it comes up in the conformality chapter that we studied.
Yeah, right. They rely on analytic continuation somewhat frequently there, right?
Yeah.
Right. So you'll tell us more about that on a week from now. But for now, we're assuming that Z0 is at the center of our punctured disk. Okay. Good. So secondly, for poles, if Z0 is a pole, this is the case of any order, if and only if the modulus of f of z tends to infinity as z goes to d0. Remember here, we're not talking about the complex point in the extended complex plane. We're talking about, because we took the modulus, we're talking about it getting arbitrarily large. Okay, so what we just proved, f of z can be written as follows. For n greater than 0, the order of the pole and g of z analytic and non-zero at z0. And then finally, to recap the last thing we said on Friday, we have essential isolated singularities, which are just completely insane, highly schizophrenic.
Did we discuss that M can only be integers?
Yeah. Remember, we made some brief comment about like the pole at z equals 0 for z to the 1/2, but that's not analytic there, right? So our insistence on analyticity for functions that have poles, analyticity in an annulus around singularities, particularly poles, mean that a pole has to have a integer order. Okay. Z naught is central singularity is equivalent to saying that the modulus of f of z is neither bounded nor goes to infinity as z approaches z naught, which is the case if and only if this amazing fact that f of z assumes every complex number as a value in any neighborhood of z naught accepting one possibility. Of course, this possibility depends on the function, possible value that it may not assume.
Are these types of essential singularities like unique to complex analytic functions?
Well, that depends on what you mean by complex analytic function.
Or, like, is there like some type of analog? Like, it seems that there are analogs for movable and poles in like your normal real.
You mean in real analysis?
Yes.
To my knowledge, no. There's not an analog of an essential singularity in real analysis. But if you go beyond what we have defined as a complex analytic function, like that is to say, a analytic mapping between higher dimensional complex spaces, there's an analog of an essential singularity. Perhaps not surprising. Yeah. So I think in general, any development you can make of real geometry in a higher dimensional sense, I think also there you don't find this behavior. But you can in the complex case. Okay, good question. So, I think we'll actually have plenty of time to give you a good impression of the residue theorem. Maybe some of the details will be a little sketchy, but I think you'll get a good sense of how it is useful to us as a computational tool. Okay. Okay, so let's make this our starting point. Let's suppose gamma a simple closed positively oriented contour, and we'll also assume F analytic on and inside gamma, except for a single isolated singularity at Z naught. Okay. So, one thing we know from this right away is that f of z has a Laurent expansion in some punctured disk around Z naught, right? Z sum from j equals negative infinity to positive infinity of a sub j and some punctured disk. Okay, so in particular, this expansion is valid on a sufficiently small circle C around Z naught. Here's a schematic diagram. Gamma. Here's my point Z naught. Here's an example of a annulus where my Laurent expansion applies. Right? This means I can find some circle C, which resides inside gamma, or actually resides inside this annulus, that my Laurent expansion applies for each point on C, right? Because it's inside the disk where the expansion is valid. Okay, good. So, if I wanted to compute the integral along gamma of f of z, it's hopefully apparent from this schematic diagram that I can continuously deform gamma to c, right? Now, I know that on C, my Laurent expansion applies. Right? So, this goes back to, remember in the middle of the term I said this example is going to come up again and again. Right? If I use linearity of contour integrals here and split this up term by term for each summand of the sequence, sorry, the series, what happens?
All the ones that don't have a power of greater than -1 become 0?
Yeah, exactly. The integral for everything that has a power of z minus z naught, where j is not -1, are 0. And for the term that just has a z minus z naught to the -1, we just get,
A -1.
say what?
A sub -1.
Times 2 pi I,
Yeah.
right? Yeah, good. Okay. So, let me remind you of a definition that I sprung on you in some earlier problem set. And you didn't see it in full generality, but here it is. F has an isolated singularity at Z naught, then the negative first coefficient of the Laurent expansion at Z naught, which would use our standard notation, a sub negative 1 for that, is called the residue of F at Z naught denoted res sub F of Z naught. A sub negative 1. Okay. So essentially, what we're going to do, you might guess, is try to calculate various integrals just by looking at the behavior of the integrand around their singularities. Okay, this is something I've mentioned many times throughout the term that we would eventually get here. And now, the last day, we're finally nearly there. Okay, so, right. Here's the theorem. F has a removable singularity at Z naught. Then the residue of F at Z naught is equal to 0. Right? This makes sense because remember what it means to have a removable singularity. You have no negative exponents in your Laurent expansion. In particular, the coefficient on the negative first term in your Laurent expansion is 0. Okay. F has a pole of order m at Z naught, then maybe this isn't so surprising, but it definitely makes our lives easier. Then the residue of F at Z naught is equal to 1 over m minus 1 factorial. Yeah, this is fine. Times the limit as Z goes to Z naught of the d minus first derivative of Z minus z naught to the m times f of z. Or, in the parlance of the last section, you might think of this as g of z, right? The function which is analytic and non-zero at z naught. Right? This is one of the characterizations of having a function, that there's some function g satisfies this equation. It's more transparent if you write it this way. I just wanted to point that out. This is like a slapdash justification that this is in fact differentiable m minus 1 times. G is analytic. Okay. Yeah.
I'm just like looking back to the partial fractions.
Mhm.
And that is the, I'm not exactly sure how to read this with the annotation we did, but it's one of the coefficients on the partial fraction expansion corresponding to the n minus 1 term, right?
Yeah, so when you do partial fractions, what you're doing is taking a rational function and expressing it as a sum of rational functions which have constants in their numerator. The constants in their numerator, if you take each sum n and come up with its Laurent expansion, it has all coefficients 0 except for the a sub negative first term,
Yeah.
right? And that constant that you come up when you produce partial fractions is exactly that term. It's just that the Laurent expansion for a rational function with a constant numerator and a polynomial denominator, a linear denominator, in fact, is just particularly simple. It just has the residue as its only non-zero coefficient. So the terminology agrees exactly, but we've said something much greater in generality here. Okay. So, just from the definition, it's like, okay, this could be useful to us somehow. But sometimes it can be a computationally daunting task to have to produce a Laurent expansion just to try to pick one coefficient out of it. Here we just produce the formula. We don't have to generate the Laurent expansion of a function. We can just calculate this value without coming up with the whole series. Get the coefficient, i.e. the residue. Okay, so the proof of this isn't long, so let's do it.
What about for essential singularities?
So I didn't say anything here. Basically, you're stuck with essential singularities. You have to actually compute the Laurent series. But when we state the residue theorem, which is the main theorem of how we use this for integration, it applies to essential singularities. Just computing the residue is harder. Not impossible, but typically just harder. Okay, good. So, right. So I already justified why the first statement is true, right? We know that the negative terms all have coefficient 0 in the Laurent expansion for a removable singularity. I'm not going to say anything else about that. So let's assume Z naught a pole of order m. Then what do we know about F? It has a Laurent expansion in some punctured disk around Z naught, given as follows: a sub negative m divided by z minus z naught to the m plus a sub negative m minus 1 divided by z minus z naught to the m minus 1. I'll write a few extra terms here, just because it may help clarify things, or maybe not. Okay, so now let's just multiply both sides of this by z minus z naught to the m. Okay, so z minus z naught to the m times f of z is equal to a sub minus m plus a sub minus m minus 1 times z minus z naught plus all the way up to a naught times z minus z naught to the m, continue there infinitely. Okay, then we differentiate m minus 1 times So remember I said in passing that we can differentiate Taylor and Laurent series term by term. So let's do exactly that. Namely, all my terms with fewer than a smaller exponent than m will go to 0, right? The first differentiation, this goes to 0, right? It's a constant. And this becomes a constant. The second differentiation, this goes to 0. And this next term would become a constant. So when we differentiate m plus 1 times, we lose the first, m minus 1 times, we lose the first m minus first terms. That is through negative m up to negative 1. I made a mistake here, didn't I? Yeah, I should have included, sorry. Of course, what I'm interested in is this, right? Because I want to compute this. Sorry, I should have included that in the sum. Okay. So if I differentiate m minus 1 times, what do I get? I get m minus 1 factorial a sub negative 1 plus m factorial a naught z minus z naught so on and so forth. Right? The factorial terms coming, of course, from bringing down the powers for each differentiation. Right? Okay? So now compute the limit as z goes to z naught. there are no negative powers of z minus z naught in the expression that I got after I differentiated m minus 1 times, which means I can just plug z naught into this expression, right? So that is to say, for every term beyond a sub negative 1, I get a 0. Right? So I just get m minus 1 factorial a sub minus 1 plus 0. Nothing, yes.
Why do we have to take the limit here as opposed to just plugging in Z naught?
Yeah, so that's what I mean by take the limit, right? Yeah, so of course if I actually have a Laurent expansion on hand, this amounts to plugging in. But when I just compute this function, I may not be able to just plug in, right? Very often, the limit will result in just an ability to plug in. But saying that we take the limit allows us to use this formula in broader generality. So, let's see. Okay, so everything we've said so far applies to functions which have a single isolated singularity inside a contour gamma that we would like to integrate around. What happens when we have multiple singularities? Well, let's draw a picture. If gamma contains a finite number of singularities, of f, I should say. Of f. And furthermore, I should say isolated. Okay, so let's say here's our contour gamma, positively oriented. And let's say I have x1, x2, and x3, all singularities of f, isolated singularities of f, say x1, x2, x3. Here's my picture. My argument breaks down because I can't shrink the contour gamma, I can't continuously deform gamma to containing just one of these singularities. But what I can do is make it so that there are essentially separate components of a new continuously deformed contour that contain each of the singularities. That is to say, I can make the following deformation. And you call these components circle 1, circle 2, and circle 3. Now, if I view this as a single contour, coming back to where I started, then the line segments cancel, right? Because I traverse both of them once in both directions. So when I look at the integral, these parts cancel, right? So that is to say, the only important the circles containing each exactly one of my singularities of F. Okay. So, this is to say, keeping this picture in mind, I can say the following. So, as usual, we'll let gamma be a simple, closed, positively oriented contour and F analytic inside and on gamma except at finite number points Z1, Z2, up to Zn inside gamma. Then we have the following. The contour integral along gamma of f of z dz is equal to the, sorry, not the 2 pi I times the sum from j equals 1 to n of the residue of f at z subject. And we've, by virtue of this picture, essentially, we're only concerned with what happens just around each singularity, right? So this is this repeated application of the method that we looked at before, which stems from our favorite example, right? And of course, this relies on the linearity of contour integrals too, right? Splitting this sum up. Yeah. Okay. Great. So let's just do a couple. I guess we should take a break. Let's take a 5-minute break, and then we'll do some examples. And then I'll just say a little bit about the argument principle. Nothing all that satisfying, just some very basic things. And then I think we'll probably finish early. Okay.
For problem 3, the one about can you make a Laurent series for square root of z? Like the 1/2. You said you couldn't, right? Because each branch cut doesn't include one radial axis.
You said no or yes?
No.
No, yeah, I said no.
It's like you can't make a whole continuous function disk that doesn't cross a boundary line. Yeah, okay.
That's exactly what I said.
Yeah.
Oh, man, that was so tough.
And since it wants the principal one, it's just the negative axis.
Yeah, exactly. gonna be, cause he says 20 minutes, but I feel like I can do 20 minutes. Right?
Yeah, I've not really started mine yet.
But,
It's gonna be kind of awkward because Luke and I are doing like pretty similar things. We're both doing the quaternions, just like different applications of them. So whichever one of us goes first is gonna explain everything about the quaternions, and the other person's gonna go up and like do it again.
oh, that's fine.
You guys are good though.
Can we also share all our homework problem solutions with each other and everybody's get extra credit? I
Yeah.
feel like that's a
Let's
smart
share
thing to
that.
do,
That
right?
sounds
Yeah.
great.
I don't think
And like
we thought that
every problem we make is an extra point.
Hmm?
Like every problem we make is an extra point for extra credit.
He's gonna put some more on the homework grid.
Yeah, do homework stuff, I'm sure.
Random numbers generated fine.
Less problems, we need more to our.
I think I'm gonna make like 2 or 3 problems.
Ditto.
Oh yeah, do we have like a time set out for the presentations?
Oh, you mean like an order in which we will
Well,
proceed?
so I have an actual final at 3:30 that day, and in class the first is like you should get there at least 15 minutes early so I have time to pass everything out.
Yeah, okay, so, based on your responses, all your responses, I thought that it was appropriate that we start at 12:30. Is that correct? That's workable for everybody?
Which day is this?
Tuesday.
Yeah, that works.
Okay, great, so we'll start at 12:30, because, I think there might be a final in the room that we're assigned to, which ends at 12:30. So we'll just go in right away and then we'll aim to be done by 3. I have to proctor an exam at 3:30 as well, so. Yeah, we can go over a little, 3:15 is fine, but you should probably leave before then. But I can just show up exactly on time, I think, that'll be okay. Yeah, so, and I'll send an announcement on Canvas about this, that, what the room is that we're assigned. It's on the 4th floor of this building, I'm pretty sure.
And how long are the presentations each again?
20 minutes, I think, is the benchmark I set, and then we should have a couple minutes per person for questions and things.
What about like food?
Oh yeah, you should be eating while you're listening.
And while you're presenting.
Yeah, I mean, yeah, if you can manage.
Extra credit?
Am I allowed to also bring in food or is that like a no-go?
Yeah, that's fine with me.
Like if I make it, is that
I think that's fine.
okay? Cool.
What do we decide on food anyway?
I think we're going with Thai. I think that was the most universally okay with everybody. Yeah. Yeah, I think I'll just get a random assortment of things, if that's okay with everybody.
Yeah, like Uber Eats to outside.
Yeah, I'm gonna have to coordinate that. I really haven't had the time to think too much about that recently, but I'll figure it out over the weekend. Make sure it happens, don't worry. Yeah. Yeah, and I haven't written the solutions for problem set 4 or 5 yet, but you know, it's not like you're studying for a final. I will eventually send them to you, just for curiosity's sake, but yeah.
What about trace evaluations?
Sorry?
Trace evaluations?
Oh yeah, fill out trace evaluations. That's another thing. Another thing I was gonna say on Canvas. Yeah, that's how the university evaluates me. So, good or bad, just fill them out. Yeah, I think it's more distressing to them, to the university, to have no responses than at least some bad responses. Okay, so
And just a question,
Yeah.
one last question.
Sure.
Are just like the people in class here presenting that day? Or are there gonna be other people also?
there's one student who is currently in China. He got stuck there. He's been not very communicative recently, but we'll have enough time if he so chooses to present. But if he doesn't, then we'll have a little extra time for questions.
Okay.
I actually was emailing him recently.
Okay,
Just to make sure that my topics didn't
Didn't
overlap
overlap,
with his, and he, I think, has chosen the topic.
yeah, he's chosen, so that much I know, but, whether or not,
That's a recording.
he's going to be able to present at the same time.
Oh, right, it's gonna be like 1 a.m. for him, isn't it?
Yeah,
I kind of forgot about that.
Right, the time difference is the main factor there. So yeah, we'll see what he says. He might just, record himself, and then we'll send that around to everybody, just so you can have the knowledge for whatever assignments he comes up with, where if you choose to do that. Okay. Good. Good. All right. So, yeah, let's do a couple examples of applying the residue theorem here. So, what if I were to ask you to evaluate the contour integral around the circle centered at the origin of radius 2, traversed once counterclockwise of the function 1 minus 2z divided by z times z minus 1 times z minus 3. So we can evaluate this using the tools that we have already developed independent of the residue theorem. But I don't know about you, I am not a huge fan of making partial fraction decompositions. There's a lot of equation solving and room for computational error if you're doing it by hand, which I am personally very prone to. So, so let's try to use the residue theorem instead. Okay, so firstly, what do we notice about our singularities of our integrand?
Only two of them lie within gamma,
Yeah, exactly, only
or only two of the denominator factors.
Yeah, only two of the simple poles, right? That is to say, our integrand is already written in the form g some analytic function at all three of our poles. And we have the power of 1 for each pole, right? So we have simple poles at the 0, 1, and 3, but only 0 and 1 lie inside gamma. Right, so they're the only ones that will contribute to the integral. Okay? So that is to say, this integral, which just for brevity I'll write our integrand is f of z equal to 2 pi I times the residue f at 0 plus the residue of f at 1. Okay, so now let's just calculate the residues. Right, so why did I bother saying that we're simple poles? Well, okay, so we're not removable. That is to say, we're not guaranteed that our residues are 0. We actually have to go to the trouble of computing them. They might turn out to be 0, but we have to compute it to find out. Which luckily we can just use this formula that we just developed, right? Okay, so residue 0, according to my formula, well, out front I get a 1 over z approaches 0 of so yeah, the 0th derivative, which is just the function itself, right? Z to the m is 1 here, right, because we're simple, times f of z. Okay, so what do we get here? This is to Luke's original point that why isn't this just called plugging in? Well, here it is, right? And often it will be, but not always. So what do we get here? 1 minus 2z divided by z minus 1 times z minus 3, right? My z's canceled, or in my function f. If I plug in 0 here, I just get 1/3. Yeah? Okay. Residue f z equals 1. Again, we're simple. Sorry, z approaches 1. So we don't have any factorial coefficient out front, and our derivative is a 0th derivative, so we're just looking at the function z minus 1 f z. Then as z approaches 1, our function with the z minus 1 part canceled out of the denominator. So altogether we get 1/2 when we plug in a 1 here. Okay, if I do a little arithmetic, make this nicer looking, if I feel like it, look at this. So, quite a bit simpler than even Cauchy's integral formula, right? That is to say, most often these limits will turn out to be quite easy to compute, to get the residues. Okay, let's do something slightly more involved. Second example. Okay, so let's calculate the contour integral around the circle of radius 5, traversed once in the positive orientation, of this function z times e to the 3 divided by z plus cosine of z divided by z squared times z minus pi to the 3rd dz. Okay, so first important thing to note here is that the fact that these functions are added together has no effect on each summand's singularities. Right? So we can apply the linearity of contour integrals here without any concern, right? And then just evaluate them separately as to regard of the singularities of each summand. Okay? So again, for brevity, I'll give these some names, because I don't want to rewrite them over and over again. We'll call this integrand G1 and this integrand G2. Okay, good. So what have I got for singularities here? 0, yeah, where z equals 0, we have a singularity. Isolated and essential. Right? Think about, just remember the function e to the 1 over z. I rushed through showing you that this is an essential singularity at 0 for this function on Friday. Which means it has infinitely many non-zero negative Laurent coefficients. Right? The raising of that to the power 3 does not affect that infinitude of negative coefficients. Nor does multiplying by z, right? That just shifts the index, essentially, on the coefficients, right? So in other words, this still has infinitely many non-zero negative Laurent coefficients. So we still have an essential singularity at z equals 0 here. What does that mean for our computation of the residue?
We have to do the Laurent fully.
We actually have to expand, find the Laurent expansion, and look at what the coefficient for the negative first term is. Yeah. Okay, how about for our G2? What are the singularities there?
0 and pi.
Yeah, there's 0 and pi, and what order are those poles, or are they removable?
Well, pi is a, oh, actually.
Yeah, this actually takes a little bit of work to do. I'll just tell you, and you should try to verify this on your own time if you're interested. These are, in fact, bona fide poles of order 2 and 3, respectively. You don't get any cancellation in the Laurent series. Okay.
Is
So-
there any way to know that without just like doing it and checking?
Yeah, you gotta check.
Okay.
You gotta check. I figured you can do that. I didn't
Yeah.
want to like take too much time in class to do that, but yeah. Okay. So in conclusion, or I should say not conclusion, but what we've surmised so far, the residue of G1 0 plus 2 pi I, the residue of G2 at 0 plus the residue of G2 and pi. Okay. So, like we said, we're stuck here. We actually have to compute the Laurent series for this function. Let's do that first. Okay, so z e to the 3 divided by z. Well, normally I would have to start from first principles, but I know the Laurent series for e to the 1 over z, right? We did that together. It's just a substitution of 1 over z for w in e to the w, right? So this is the same as z times sum from j equals negative infinity to positive infinity of 1 over j factorial times, now I substitute in 3 divided by z instead of 1 over z, right? 3 over z to the j. Okay. And you might have been somewhat mystified why whenever I wrote a Laurent expansion before, I wrote out the first few terms, or I wrote out some terms, just because getting good practice in that, when you have to compute a residue, you want to be able to just write out a few terms of a series so you can get to the negative first term. Right? So, I mean, what do I get here? Z plus 3 plus 3 squared over 2 factorial divided by z. In other words, I just, yeah.
The factorial isn't defined for negative integers.
Oh, is that kind of easy?
Oh, yeah, you know what? You're right, you're right. Also, this makes no sense. That doesn't agree with what I said before, right? The Laurent expansion for e to the w starts at 0.
Oh,
Yeah, sorry. My mistake there. And also, we don't sum infinitely to the left in that case, right? Okay. Good, thank you for that. Right, so then I multiply through by z, and this is what I get. So, implies residue g1, 0 is just 9 halves, right? 3 squared over 2 factorial. Okay. So, now, taking my word for it, that these are poles, and for G2, we can just use our formula, right? The limit of the first derivative here and the second derivative here, right? Because the number of times you take the derivative is 1 less than the order of the pole. Okay, so residue G2 at 0 is equal to, so we get 1 over 1 factorial. I'll just write out because it's good to see, to remember the formula, right? Times the limit as z approaches 0. The first derivative of z squared times g2 of z, which is just limit as z approaches 0 of dz of cosine of z divided by z minus pi cubed. Okay, so here's probably the hardest thing about making this computation. You have to apply the quotient rule here. Okay. Okay. What do we get from applying the quotient rule? I'll just tell you. Yeah. But you're really fast at derivatives. Verify that. I'm pretty sure this is right.
Z to the 6th on the denominator.
Ah, but I canceled some terms. Right? This should be a z to the cube. Yeah, and this would have a z squared. I'm sorry, z minus pi squared. Right? So I canceled the z minus pi squared from the numerator and the denominator. Good. Good. So okay. Right. So you just plug in 0 here, and what do we get? Yeah. Negative 3 over pi to the 4th. Yeah, good. Okay. So finally, let's calculate the residue. again, if you take me on my word, is truly a pole of order 3. Right? So, what do we get? 1 over 2 factorial, limit as z approaches pi of the second derivative of z minus pi cubed g2 of z equals 1/2 limit as z approaches pi of the second derivative of cosine z divided by z squared. Okay, now we apply the quotient rule twice. I don't know if you care about verifying whether I'm right or not, but you should know that this is a annoying but very tractable process, right? So what do we get? This is what I got. I got 6 minus z squared cosine z plus 4z sine z divided by z to the 4th. Okay. Which, if I just plug in a pi, what do I get? I get negative 6 minus pi squared divided by 2 pi to the 4th.
Oh, yeah, 1/2.
Yeah, I had a 1/2 out front. Okay, good. So altogether, I can say my integral evaluates to this. It's not pretty, but it is a numerical value. Okay? So, suffice to say, you would spend a lot more time trying to compute this if you tried to use almost any other method. That wasn't the fastest thing ever, but it was faster than any other way you could do this by hand. Okay. So, we got about 10 minutes left, and I'll leave it up to you. Do you want to hear a little bit about the argument principle, or would you rather just call it? It's up to you guys.
I want to hear more.
Okay.
Before we do that, I feel like my brain's a little exhausted. Why is the residue on G1 of 0 equal to 9/2 based on what we wrote?
Oh, it's just the coefficient on, it's for, for negative
Yeah,
one.
okay, yeah.
Yeah, for the power negative 1.
I was looking at 3 squared over 2 factorial and it just was not 9/2 for me.
Okay,
But yeah, okay, that makes sense.
cool. All right, so I'll tell you one lemma, and then I'll tell you what the argument principle says with nowhere close to a satisfactory justification for it. So the argument principle is essentially tells you how to integrate the logarithmic derivative of a meromorphic function. Okay, so What is a meromorphic function? F is meromorphic in domain D if every point in D, F is either analytic or has a pole. Okay? So somehow we don't really care about what happens at removable singularities because it's essentially like a trivial thing to change it around to be analytic at that point. And we're also discarding the highly pathological behavior of a essential singularity. So if we only have analyticity and some poles inside D, then we're called meromorphic. Now, here's the surprising thing. Just from this definition, we can say the following. If F is analytic and non-zero on a simple closed contour, C, and meromorphic inside C, then F must have a finite number of poles which we denote n sub p of F and of zeros. N sub 0 of F inside C. There's no finiteness assumption in the definition of meromorphic, but if I can find a contour that satisfies this for my function f, I'm guaranteed to have a finite number of zeros and poles. Okay. Here's a sketch of why this is true. The singularities of F inside C are isolated. Right? That's part of the definition of being a pole. Right? This follows from the assumption that F is meromorphic inside C. Okay. Then by something called the Bolzano-Weierstrass.
Oh no. Oh. It's bad.
Yeah, this is not pleasant, maybe. Brings back bad memories.
Oh, yeah.
Well, what does this say?
The part where I don't remember. It'll take me
if you don't like to recall it.
Okay, I'll just say, this says, every infinite sequence
Oh, is this the subsequence?
in C, yeah,
Yeah.
every infinite sequence in
Convergent
C,
subsequence?
yeah, has a subsequence. That converges in, to a point in or on C. That is to say, either inside or on C. Okay, so, therefore, what can we say? If F had an infinite number of poles inside C, then some subsequence converges inside or on C. To a singularity. Right? This is owing to the continuity of F. Right? Singular, singular, singular. I'll stay singular as I get to the point of convergence. Okay? Right. Which will not be isolated. Right? Because we have this sequence of singularities that converge to a singularity. So it's not isolated. It can't be a pole. Contradiction. You can argue a similar but slightly more complicated argument for the zeros. Okay? It again relies on the Bolzano-Weierstrass theorem. Okay, so this is barely an argument. Let me just tell you the statement of the argument principle. F analytic and non-zero on positively oriented simple closed curve C and meromorphic inside C. Then one over 2 pi I times the contour integral around C of f prime of z divided by f of z dz is equal to the number of zeros of f minus the number of poles of f. Zeros and poles counted with multiplicity.
This could have been used in the last homework, right?
We showed the first part.
Right, yeah.
Yeah.
What problem?
I just drew over.
3, maybe, I wanna say.
There was, we'd like show the logarithmic derivative, or the integral of it, was equal to the number of zeros inside of.
Oh, yeah, when you're analytic, right? Yeah, right, which is a corollary of this. So yeah, you're right. Yeah. So, how do we prove this? This is a logarithmic derivative, right? This is to say, like, if you look at the function log of f of z and take the derivative of it, you get this expression, f prime of z over f of z. So that's basically what you're doing. You take that point of view and you look at some segment of the contour C that doesn't hit the branch cut of log, and then you keep track of the span of the argument that gets traversed, and somehow count something using the residue theorem. This is a consequence of the residue theorem and the fact that we can do something clever to avoid the branch cut by just traversing part of C. That's not very meaningful, but if you decide to look at the proof, maybe that will help you a little. Okay, so great. I'll see you all on Tuesday of next week in a room that I can't remember the number of, but I'll send to you over Canvas. And yeah, don't forget to submit the last problem set sometime before midnight tomorrow night. Okay. Have a good finals period up to when we have. Yeah, you too.
What class is he in the Bolzano?
What was that thing you were talking about at the beginning of class? That you should do evaluate,
I actually remember the more on because we use it all the time, but the proof is like 2 lines. But
Yeah,
put like so
so,
much other stuff before we use the proof. So it's kind of
The
funny.
first example of that
It's the first named theorem in the book, but it's like 2 lines.
if you have
It's like
a integral of a rational function that has as inputs sine and cosine from 0 to 2 pi, you can think of that as a contour interval in the complex plane traversing the circle once. And you basically think of that rational function as like the real or imaginary part of some. Basically, you substitute in the complex functional equations that we have for sine and cosine into that real rational function to get a complex function, and then you integrate around the contour circle that contains all the relevant data from 0 to 2 pi. So yeah, more or less that. There's more details, but yeah. So the residue theorem allows you to calculate integrals of certain multiple valued functions. It allows you to calculate integrals, all kinds of real improper integrals that may or may not have to do with trigonometry. But yeah, there's a lot of applications that unfortunately we didn't have time to talk about. But
Yeah.
it's the bulk of chapter 6 of the textbook, if you feel like looking at it.
Okay. And do you have any resources to help understand, like, what we need to do problem 2 in the homework?
I mean,
Like, any parts of the book that are helpful, like, any
Was that
resources on, like, convergence or anything? Because I never actually took Calc 2, and, like, so I self-studied all the convergence stuff, and I didn't really, like, look too formally at any of it.
yeah. You ever go to Paul's online math?
Yeah.
Have you looked at that for
Yeah.
some of the series and sequence stuff?
Years ago, yeah.
Okay, so that might help if you look at some of the,
Okay.
like, just the lecture parts.
Sure.
Because they're pretty fast reads, they're only a couple pages long, but they give you a pretty good basic.
My friend is obsessed with Paul's.
I mean, they're good. I don't know if it warrants obsession, but
Well, he does what? Calc 1, 2, 3, different view. That's really it.
Yeah.
Maybe some
My
linear
notebook
algebra?
has anything on this convergence stuff, I'll send that.
Okay, yeah.
Yeah, you can probably find, Rudin Rail Analysis for free online. That was the book I learned all that stuff from when I was an undergrad. Thought that was pretty good. But, yeah, there's a lot of stuff about the difference between uniform. I hope it wasn't confusing the term pointwise convergence. That's just the standard notion of convergence that we usually talk about. But yeah, the point is that, when you're looking at the entire radius of convergence, the entire domain of convergence, is that as you approach, you can't be independent of the point as you converge, right? So for any closed ball, you can fix an upper bound that doesn't depend on the point that you're at. But as you get closer and closer to the boundary of closer and closer to the circle of convergence, as they say in the textbook, then you become so that you can't be independent of, you can't converge, you can't come up with the constants that prove you converge independent of the point that you're at.
I don't think I'm following too much.
Okay. Really try to understand the difference between pointwise and uniform convergence, and then I think then it should become a little more clear what I mean by that.
Okay.
So like uniform convergence loosely means that you can come up with these bounds, these epsilons, that are independent of the point at which you're choosing to prove convergence, right? It's true in the entire closed subdisk, right? So as you get closer and closer to the circle of convergence, this place where you necessarily have to fail to converge at some point on it,
Yeah.
you lose that independence of the point you're at for convergence.
Okay, yeah.
Okay.
But it can still pointwise converge.
Yeah, so that's the point. It still converges, but not independent of the point at which you're checking the convergence.
Yeah, okay.
So do some reading on the difference between uniform and regular convergence.
Okay,
And then
sure.
hopefully this discussion that we just had will be helpful.
Thank you.
Yep.
Have a good one.
Just, I feel like I'm missing something about that problem, but it's it's like a one-liner, right?
Yes.
Good.
Yeah. You know, the reason I included that is just because like in the textbook, it's
Yeah, that was the
it's
first
like, why?
sentence, yeah.
Yeah, it's like this is easy to just like fill in the gap of.
Okay.
Yeah, don't worry. It's not hard.
Okay.
I think people are just a little intimidated because they're like, oh, I didn't really study convergence that much. It's like, well, just look at the definitions. It's fine.
Okay. All right, thank you.
Yeah, see you.